Y listo. Muy bien, buenos días.
Buenos días.
Vamos a iniciar. Bien. Okay, so pase. Okay, so sorry for that. So let's start now. So remember from last time, we proved this result. This one here. Or at least we proved it when M and N were in Euclidean space. Right? So one of the motivations for this is that we have another way of creating new manifolds. We saw several examples, and we're going to see more of them, right? Now, of course, the statement says that we have a regular submanifold, but we prove that a regular submanifold is a manifold on its own. So we have examples of manifolds. So let's see this. This one, we covered that one last time, but again, I'm going to go through it. Maybe it was too fast. So I have this function, which is a polynomial function. So definitely it is a smooth function. And so let's try to understand this function and see if we have. So we're missing one, Salvador. He was here a while ago. Well, let's continue. This is still a review from yesterday's class. Right, so we have this function, smooth, and let's try to determine what are the critical values, regular values, and at the same time critical points and regular points. Because we are in Euclidean space, we have the standard coordinates, so we can take the partial derivative, and that's what we get here. So we know that this is the partials. Hence, we can now decide which points are critical points and which ones are regular. So for any value c, distant from 0, we have a regular value, right? Because the preimage is going to consist of points whose partial derivative cannot vanish, whose every partial derivative cannot vanish. So we have no critical points. The only critical point of this function is the 0 vector. And that point is mapped to 0. That's why we're removing 0, and any other value is going to be a regular value. So from this result, we have that the pre-image is going to be a regular submanifold as long as C is non-zero. Moreover, you know very well what is this. So this is the sphere of radius C, right? Well, it is the n-1 dimensional sphere. So another proof that the spheres are manifolds. Now, oh, and finally, I forgot to mention here, I mean, it's something that we know very well, but the whole idea of this is to use the theorem. The dimension of the sphere is going to be n-1. Here it is, of okay. Great. So let's move to the next example. This is something that we have seen before. We have already seen the definition. And remember that there was also a homework that I was asking you what is O1 for n equals 1 to find this group. Okay, so let's consider the set of all n by n matrices with real coefficients. We know that this is Euclidean space, Rn squared. And I'm going to take another manifold n, the set of all matrices that satisfy this condition. And this is precisely the set of matrices that are symmetric. Okay? So now, let's try to figure this out. What do you know about this set? The set of all symmetric matrices. What can you tell me about it? What algebraic structure do you think that this set has?
It is a group.
A group under which operation?
Under multiplication or multiplication of matrices. No.
Really?
Perhaps not. Give me a sec of mode. Sorry for that. On the addition, clearly it's a group.
Come again?
On the addition, clearly it's a group.
Under addition, right? So, but not only a group, so it is true, but it is a vector space.
Yes.
So under addition is closed, and if you multiply by a scalar, it is also closed. So this in fact is a vector space. So this is the answer, it is a vector space. Now, what is the dimension of that vector space?
N squared.
The same one here. So let's see. For a symmetric matrix, so you can put any number here, here, all the way up to n. So far you have n parameters on the diagonal. But if you put something here, you are also filling out this one here. If you put something here, that means that you're putting something here. So how many parameters do we need to determine a symmetric matrix?
The sum of all n from 1 to n, which is n times n minus 1 over 2.
Right, so that's n times n minus 1 over 2, right? So that's the dimension of the vector space of n by n symmetric matrices. Nice. Okay, now I'm going to consider this function now. First, we must verify that this is well defined. And that function is symmetric. Because if you apply the transpose by the properties, you will get exactly the same. Right, so this is a well-defined function. Moreover, this is a smooth function. You can remember that the matrix multiplication is just a polynomial on the entries. Right? So we have a smooth function between Euclidean spaces. And I claim that the identity matrix is a regular value. Right? The identity matrix is here, is symmetric. So the reimage of that is going to be exactly what we are. This is ON. And I would like to argue that ON is a manifold. I can see ON has the preimage of the identity matrix. And then all that I want to do now is to show that the identity matrix is a regular value. Let's do this for n equals 2 only. Right? Up here, when n equals 2, I get I don't get 3. What am I doing wrong? Oh, so maybe you said it correctly and I wrote it wrong. It's n times n plus 1, right?
Simple.
I mean, because what is a 2 by 2 matrix symmetric? You put A, B, so you need 3 parameters. Yeah, so sorry for that. Here is a plus. Mhm. Okay, then. Right? So let's specialize to the case n equals 2. So I have a map from the set of all 2 by 2 matrices to the set of 2 by 2 symmetric matrices, which is given by this formula. Right, so here I have already computed A times A transpose. It will look something like that. Okay? Now, remember that I want to show that the identity matrix here is a regular value. So let me write down F in terms of the entries in our tree so that I know what are the coordinate functions of F. So I'm going to write it like this. I'm taking these elements to be my basis of this vector space. And with those coordinates, F have these coordinate functions, F1, F2, and F3. Right? And then so in order to determine the regular values or regular points, critical points, because I have a map between Euclidean spaces, I just take the partial or the Jacobian. Okay, now I'm labeling this as x1, x2. Those are my coordinates on the set of 2 by 2 matrices. Right, so when I take the derivative with respect to A, I get 2A. This is only F1. And then with respect to B or X2, and then 0 and 0. Only for this function. Okay, so in that way, I get the Jacobian that looks like this. So this is what I have computed, but you can look at F2 and F3 and compute the other two rows. Now, so the whole idea is trying to see what is the image or the rank of this matrix at every point. In particular, at points that are mapped to the identity, right? So, because we want to use this result. So, in order to be a regular point, the differential has to be surjective, or this matrix needs to have rank 3 at every point in O2, right? Now, so I mean, definitely this matrix doesn't always have full rank, I can take X to be the zero matrix, and I have the zero matrix on this side. Okay, remember that this represents a matrix here. So that will be the zero matrix, and then the Jacobian will be zero. So I only care about matrices in here. That means that this equation must hold for this matrix. And that will lead us to three equations. So what I want to show is that for x1, x2, x3, and x4 that satisfy these three conditions, this matrix has rank 3. Okay? And well, this is something that you can work out. For instance, x1 and x2 cannot simultaneously be 0. The same x3 and x4 cannot be simultaneously 0. So in that way, you have at least rank 2. Now you have to use this to say that you have rank 3. Okay? So this is not very appealing, but that's a way of doing this. And so I wrote here the same matrix. So you can prove that it has rank 3 and you're done. Right? So this is how you can prove that O2 is a smooth manifold. Later, I don't know if by the end of the class or next week, we will use another result that we will be able to show that ON is a smooth manifold. So here you can see that there were many computations. It is a little bit involved, but at the end we can do it. We will see another way of showing this. Now I forgot to mention here. Let's use the theorem. Assume that this and this is true. Then what is the dimension of ON? Is the dimension of n squared this dimension minus the dimension of this one here. And what is that? So what is it?
Tuyến.
Is
No.
that this?
Yes.
Okay, so that's the dimension of ON. So for n equals to 2, what we got was some dimension one, right? Okay, so as you can see, it was very much involved to show that O2 was a manifold, right? We picked up a basis. It was good that this was a vector space, Euclidean space. Then we have the coordinate functions and do calculus to find critical points and regular points. Okay. So again, we will see this later on. Now let's see another example, SLNR. Right? This is the set of all n by n matrices whose determinant is 1. Remember that GLNR is an open set, hence a manifold. And I'm going to consider this map. We have seen that that's a smooth map because it is a polynomial function on the entries of x. So this is a smooth function. And I would like to see that the one here is a regular value. And in that way, I will have that this is a manifold. Because the pre-image of 1 will be the set of all matrices of determinant 1. So I'll be done once that I show that the determinant, that 1 is a regular value. We will proceed in the same spirit as the previous example because we are on Euclidean space. We will take partial derivatives and show that they would never vanish on the level set. And that's enough because the theorem that we are studying is maximum rank. Here rank is 1. Okay, so I'm going to denote my xij the coordinate functions of Euclidean space. And this is wrong. This is not true. Not for all I and j, but for at least one, right? And that will show that I have a regular value. So that's wrong. I mean, this is evaluated at some matrix. So if we find one value that is non-zero, then we have the point is not critical, hence regular point. Now we're going to remember a way to compute the determinant that is very useful for this result. So remember that f is the determinant of x. And the determinant of x, I can write it like this. Basically, what I'm doing, I wrote it I'm expressing this in the J column, right? So the determinant is this entry plus the determinant of this smaller n minus 1 n minus 1 matrix, right? So that's the definition that I'm using. Like something that you maybe saw for our tree. It is this times the determinant of this matrix, and then minus this number, the determinant of this, and this, and so on. So that's the formula that I'm using here. So the Sij's is the determinant of that smaller matrix. Okay? So that's how am I writing this. So there are many ways to write this, the determinant, and that's one. And this one is useful because if you want to consider a special coordinate function, let's say x1, y1, in the determinant, it is only going to appear here. In no other place will you find the x1, j entry. Only there. Again, remember the rule. This times this. And then this, and so on. This. So these entries only enter once on that formula. So that's very important to keep in mind once that we take the derivative. So if I take the partial derivative of f, I get precisely the determinant of the smaller n minus 1 times n minus 1 matrix, right? So that holds for any entry, right? Now, well, I forgot to evaluate this on x. But now x is non-singular, then at least one of the Sij's must be non-zero, right? Because I'm assuming that x is non-singular. So that's impossible that all of the minors you have determinant 0. At least one of them is non-zero of the minors. And that's how we prove that x is a regular point of f. Hence, I have this manifold. N squared minus 1, n squared 1. Okay, so that's how we prove that SON is a smooth manifold of dimension n squared minus 1. Is this clear for everyone?
Do you mind repeating it
Pardon?
again? Do you mind repeating it?
Right. So let's see. You have a matrix, an n by n matrix. Then look at the set of all minors, n minus 1 times n minus 1 matrix, right? All of them. There are many of them. Remember that, and then if you want, you can look at all of the smallest one. A matrix is non-singular if at least one of those is non-zero. Let's do it 3 by 3. You compute the determinant like A times, like this, right? And then you go minus D. So this will be Vi minus CH plus G Vf minus Ce, like this. So the first thing, I did it this way, but it is important to keep in mind that you can do it for any row or any column, right? And what is important is we actually use all of them because you see the A only appears one. There's no A here, no A here. When we take the derivative with respect to A, that's very important. For instance, if I would like to take the derivative with respect to H, this expression is not good for me because I have an H here and an H here. So for H, it is better to use either this row or this column. Okay? So that's the first thing in order to conclude this. The derivative is going to be this number here, the determinant of that minor. Right? So that's the first expression. Is that clear so far?
Yes.
Okay. Now, so for this, I don't care if the matrix is singular or not. It holds for any n by n matrix. Here, so far, so good. No restriction whatsoever on the matrix. Right? Now, let's now use that fact that X is non-singular. X being non-singular means I don't remember if it's if and only if. Well, maybe if we put it like this. I don't remember how do we see this in linear algebra. X is a square matrix, n by n matrix. To have rank n means if you take any smaller, any one, you will always find a 1 by 1 matrix which is non-zero. You can always find a 2 by 2 matrix of determinant non-zero and so on. Well, it's not every, it's at least one. I don't know how to put it. Do you remember this result? Because I mean, I only care about the minors. This is what I'm using.
There exists at least a principal minor such that
Right.
it doesn't manage.
At least one. I mean, because if all of the minors vanishes, then you cannot have rank n minus 1, let alone rank n. Okay? So that's what I'm saying on this step here. At least one. Right? So that's what I'm having here. Okay. What I'm having trouble is the if and only if part. Because I'm thinking about this matrix. So you have, I think it is true, but a 3 by 3 matrix. So that minor has determined non-zero, right? But for instance, if I put here a 0, that's why I'm having trouble. What is the right condition here about the if and only if? But it must be true. Okay then, so there are 2 steps. This is for any matrix. Well, I cannot erase that anymore. So there are 2 steps. First, for any matrix I have that, which is important that I can isolate one of the entries, and that allows me to compute this. The second step has to do with x being non-singular, and I can find at least one minor or determinant non-zero. And that's what I use to say that x is not a critical point, because at least one partial is going to be non-zero. A critical point is every partial derivative equals to 0. since here we find at least one that is non-zero, x cannot be a critical point. It must be a regular point. So up to here, Moises? Moises?
So far, so good.
Sorry?
So far, so good.
Okay, right. So 2 steps, first the partial, and then to assure that at least one of them is non-zero. Right. And what I'm going to say later on, this is very important, okay? So I want you to understand everything that is going on here. Right, so what I have now is that the identity is a regular value, hence the preimage is a regular submanifold of dimension n squared minus 1. Okay? Now, precisely this is all of this is what I want you to have clear understanding of this. Because remember the theorem that we're using. I only care I have M, F, N. I take a point here. I look at the preimage. The theorem that we're using requires us that at every point here, we have a maximum rank, right? That's what we're using. At every point here, maximum rank. Every point here, maximum rank. And then we have that it is a submanifold. The argument that we have here, we have proved more than that. Even the points that are not in the preimage have maximum rank. In other words, in this step, I only use the fact that x is non-singular, and I don't use the fact that the determinant of x is 1. It has to be 1 to be on the level set. But I don't use that. I only use the fact that the matrix is non-singular. So in other words, I'm showing that every point is a regular point. For this function, the determinant, the phi on GLN. Every point here is a regular point. Okay?
All right.
Now, think about this. Remember that lives in Euclidean space. And you have a smooth function defined there. And you don't have any critical points. So this is another way of proving, which is not the right way, that this cannot be bounded in Euclidean space. Because if it is bounded, then basically you will have a maximum and a minimum, and that will give you critical points. So remember what we saw yesterday with the height function. These were critical points. On the sphere, the height function critical points, right? The pre-image, are some manifolds. In this case, are all circles. In this case, the pre-image is either a circle or two circles, right? That's what we proved yesterday. So more or less what we have here in the previous example is something like this. It's like a cylinder, so to speak. You can either say that it goes to infinity, or maybe it doesn't go to infinity, but it doesn't contain this because it is a manifold. Okay? You cannot have the upper circle or lower circle because the manifold that we have seen, they don't have boundary. Okay? The function is the height function. So you can think this in R3. You have the height function just project into the C entry. And in that case, you have no critical points. The pre-image of every point is a circle. And that's more or less what we have with GLM. The pre-image of any point in the image will give you a smooth manifold. Okay? Now, we don't care. I mean, you should wonder, well, why not I take the pre-image of 3, even of 0? I don't know. Well, I mean, you can do that and you will get smooth submanifolds here of dimension 2n squared minus 1. But what is special about F1 what is special about this is that that's going to give me a group. So that's the difference between that one and all of this. Because the pre-image of 1 is going to give me a subgroup of ELN. And the other ones are nice manifolds, yes, but they don't have the structure of a Lie group. So that's basically why we only care about 1. Okay, so basically this is it about this result, the one that we proved or partially proved yesterday, this one. That the differential needs to have must be surjective, and then the pre-image, we are done. So with this result, we can get examples of very nice manifolds. Sometimes it's very complicated, like this example that we worked out. So there is another more useful result that is going to give us manifolds. Okay? So let's try to see this. So as before, we have a smooth function. And then we know that every time that we have a smooth function at a point, I have a linear map, and remember that we solved the rank, right? What is the rank of a function at a point? Is the rank of this linear map. And remember that this is local information. It varies from point to point. It can vary from point to point. Okay, so before stating the theorem, I'm going to review a couple of examples that are very good to know. I'm going to make very particular maps just to show you something nice and then what can go wrong. So let's consider a map between R2 and R3. Very basic function is just putting the plane in the XY plane in R3. That's my function f. R2 inside R3 at level 0. Now, this is basically multivariable calculus. So what is the differential? So let's put xy, the coordinates on R2, R1, R2, R3, coordinates here. And basically what you're doing is this. That's how the differential looks. Yeah, I use different coordinates just to try to make it clear. But it should be like this. This is enough to show you that they are different. Right, because one is in R2 and the other one is in R3. But I just wanted to make more emphasis, that's why I choose different notation for the Cartesian coordinates. So that's the differential. Again, you can compute the Jacobian of this, the matrix, and you will have 1, 1, and zeros everywhere. Now we care about the rank. So in this case, basically this is independent of the base point. So we have that this has rank 2 at every point. It has constant rank. And this is something that we will use in the theorem that it is ahead. We will require the function to have constant rank. Okay, and this is what we're doing. Very nice, the plane sits inside. Now, the next problem is the plane trying to put it inside R3 in a very strange way. But in order to do the drawing, I will instead do it in R1. Okay, so, and I think it is best if I put this interval here. I would like to put the line 0 infinity inside R2. We can do it very nicely as in the previous result, right? Okay, that's done. But the way that I would like to And this is a problem for you. So this is my function. This is 0 infinity, assume that here is 0. Here is R2. So I want you to do this, but like this. This is not so important, but assume that 0 goes to the origin. The function that you need to come up with, I want you something that goes around. It approaches the unit circle, but it never touches that. So again, maybe here is slowly. I don't care. But what I care is that it becomes closer and closer to the unit circle, but it will never touch it. So I need ideas for a function like that. So without giving the explicit formula, what kind of approach will you come up to solve this?
Something in terms of sines and cosines.
Right, so it is best to use polar coordinates. Yes. So in order to go around,
It's gonna be like the circle.
come again, Jesus?
For example, the line that makes the circle, like r times cosine, comma r times sine. When instead of using r, we use 1 minus e to the minus t.
But I mean, basically, just tell me what is R. How do you?
Yeah, sí, sí. R
Right,
de
because
t.
with
Like,
this, go ahead.
Yeah, we're using complex things.
Because so far, this will just help me go around as many times, no problem.
Yeah.
Now I would like the radius to be approaching 1, but it's never 1.
Like the radius can be given by 1 minus e to the minus t.
Sorry. 1 minus
E to the minus t.
like this.
Yeah.
Let's see. I don't know. So this is E of t, right? And then
Yeah, like when t is small, then e to the minus t is almost 0.
wait.
It's almost 1. I'm sorry.
T is small. You mean
Close to 0.
here or oh okay. When t is here, you're saying.
Yep.
When t is 0, no, yeah. When t is 0, you're close to 1. No.
Yeah, that is why we have 1 minus.
Yeah, but But I think you are doing the opposite, right? When I'm approaching 0, I think that you are approaching the yellow circle.
I know that's why it has the e to the minus t, because at t0 it has e to the 0, which is 1 minus 1.
Right.
Then it starts at 0 and it starts growing because we are approaching. We're getting. I don't know. No, yeah,
Yes,
we're
right.
getting.
I mean, when t equals 0, you have 1. But that's exactly what I'm saying. So maybe just what I had in mind is different what you're saying. I was saying start somewhere. Start, I mean, from 0 and you increase. So when you're very far, you are very, very close. And I think you are very, very close when t approaches 0, right? You have the other.
No. 1 minus e to the minus t is decreasing.
Right, so you start very close and then you pull away, right? I think is this or not. You start very close to the blue circle inside. It's smaller than 1.
I mean, the e to the minus t is indeed 1, but when we subtract 1 minus e to the t, that goes to 0.
When t is 0. Oh, right. Sorry, right. When t is 0, you're 0. Right. No, I had it wrong. Yes. Okay. Remember, here I omitted 0 because the half closed interval is not a manifold. That's why I'm removing 0, but we can use it just to understand what we're doing. And what you're saying, that's correct, right? 0 goes here to the origin. Yes. Now I get it. Nice. And then, so you have something like this. So I don't know where does it start, but it moves all the way, blah, blah, blah. Okay? Okay, so this is the function that I have in mind. Very good. Now, the function is 1-to-1, right?
Yes.
This is a 1-to-1 function. Nice. Again, you can see that the constant rank, it has constant rank and it is equal to 1. Okay? Nice. Now, by doing this will also give you a way of a two-dimensional model. The plane wraps inside a cylinder and then approaches the cylinder. Okay? So that will give you another example, but in 2 dimensions. How the plane wraps in 3-dimensional space to a cylinder. Okay. This is very nice. This is later going to be an example. I'm talking about what you have here of when we see embedded submanifolds. Okay? So this will be very, very interesting. And actually the problem is what is happening close to the line, to the unit circle. What is happening close to the unit circle is the same that we saw yesterday. Remember? But instead of the circle from yesterday, we have this line, this segment. So it is approaching very much, and it is moving up and down. So we lost Jesus again now. The same with the circle. We're going around, and each time we're getting closer, closer, and closer. So this is a nice example. And again, the important thing, this example with the same principle in higher dimensions. The plane wrapping inside a cylinder and approaching the cylinder. Okay. So these two examples, so to speak, we are moving in. We have like an inclusion, so to speak. Next, I'm going to see the opposite, which corresponds to a projection. Right, so here, the domain had dimension less than the codomain. The same here. Now I'm doing the opposite. The domain has higher dimension. Good. Okay. So again, we have coordinates. The same reason I shoot it differently, just to understand a little bit more. And the push forward looks like this, the differential. Or again, if you use the same coordinates, we have F lower star at X, Y, and Z. Like this, right? Now I'm using the same notation here. X and X. Right? In this case, the function is not injective, but it is onto. But the differential has a kernel, okay? And so we have constant rank 2 at every point, okay? So this is just the example that I wanted to illustrate. Here, if you would like to use the theorems that we saw yesterday, the pre-image of a point is going to give us a line. Has a manifold, 3 minus 2. And for any point, because all points are regular here. Okay, now, so this is the second approach to coming up with submanifolds. It relies on a result from multivariable calculus. I don't know if you have seen this, so we will discuss this. I don't have any proofs also. Okay, so you have a function like this. You have a function, you have a point, and you assume that nearby P, all of the points will have the same rank. Okay? Same rank. Now, so at this point, basically this condition is replacing what we had before of a regular value, because for regular value we're required to be onto. So here we are relaxing that condition. I don't require that the differential be onto, but I'm requiring that the rank remains the same. Okay? So, Salvador, ¿tienes problemas de conexión?
Sí, me está fallando mucho el modem estos días.
Okay. Okay, then, so let me recall what we had before yesterday. This means that at every point on M, the differential is surjective. So I have, it's a very specific constant rank. It has to be all. So here, I'm relaxing that condition for constant rank in the neighborhood of the point. And that's the only condition that I need. Okay? Then, if that holds, you can find the geomorphisms. Maybe this G is smaller than this neighborhood when it is constant rank, okay? But there is a diffeomorphism in the neighborhood of P, and also a diffeomorphism in the neighborhood of f of P, such that you can write this function like this. So that's why I was talking about this example, right? We have constant rank, like this is the most basic one. So here I have constant rank 2. Okay? So I'm writing the function f, basically. I'm finding local coordinates around P such that f looks like this. Oh, here K is the constant rank. I missed that one, sorry. I'm going from Rn to Rm. Okay, I don't know if you have seen this result before.
I haven't.
Okay, so we're not going to see the proof today, but so I will try to have it for next class. This comes in the appendix, and basically we will do the very basic ones, making the smallest values and see what's going on. Okay, then so this is basically this is the same statement, but for manifolds. It's exactly the same. So there's no problem here. Right? F constant rank in a neighborhood, you can find charts, which is given by the result in multivariable calculus that I stated before, and you have this. Okay, so maybe next time we'll prove this. This we will not prove it because it is based on the other one. But this is the important one, this one here. I have a smooth function, I have f, and then I look at the preimage of f. Right? Now, the result from the top, what we saw yesterday, requires that at every point here, the differential must be onto. Right? That's what we saw yesterday. So this is different. This is telling me that, okay, I want in a neighborhood you have constant rank, and then it is a manifold. So in principle, I need to prove more, and then I will know that I have a manifold. Okay? It might look more complicated or harder, this result, to use than the previous one, but it happens that it's not. It is much better this way than the previous one. For one thing, note that so the differential doesn't have to be onto, right? And that's a big difference. And this is something that we saw when we were trying to see that ON is a manifold. To prove that you have a regular point, you want the differential to be onto. So we even look at basis, at the tangent space, to show that it is onto. So it happens that when we use this, it is much easier to prove that something has constant rank than to prove that it is onto. Okay, and so this is what this theorem is stating. I care that you are able to use it. The proof of this will come tomorrow. Next time, sorry. But I would like to use this. Now, something that maybe I haven't mentioned is the codimension. So you have a manifold of dimension n and S, a regular submanifold. Of dimension R. So the codimension of S in M is just the difference. So that's the codimension. The other direction that you're missing, so to speak. So this has codimension K, meaning the dimension of that is N, the dimension of M minus K. Okay then, so I want to use this to prove this. Okay, so at the beginning of the class, we argue more or less how to prove this for n equals 2. But here, we would take a different approach. So, first of all, I need a map between manifolds, something that the pre-image will give me ON, and hope that I have a constant rank. So I'm going to take this map. Notice that it is very different than from the one that we had before. Okay? So from GL to GL. Right? If X is non-singular, this one is also non-singular. Moreover, recall that this is inside Euclidean space. And also this function is infinity because it is polynomial on the entries. So I have a smooth function. What we had before, remember that here we used the n by n symmetric matrices. That's what we did before. So we're replacing now this. But again, the pre-image of the identity will give me ON. Okay, now let's do the following. Take two matrices, two non-singular matrices, A and B. And let's compute this. By definition, I have this, and then properties of the transpose. And again, I use the definition of F. You write it like this. And this, I can write it down like the composition of these three functions that we have seen before for Lie groups: left multiplication and right multiplication. Okay? Now, so I have three functions here. Let me now rewrite this also. This can be written like this. Hence, I have this formula. And that formula holds for any matrix A that it is non-singular. Right? Well, let's compute the differential of f using this identity here. Right? So the left-hand side is this. I'm computing the differential evaluated at V. I use the chain rule and I have this. On the right-hand side, I put V, then goes this, and this. Okay? Is that identity correct for everyone? So here A and B are arbitrary matrices. They are non-singular. Now, but we have seen that this map and this one, left and right multiplications, are diffeomorphisms of the group. In particular, their differentials are non-singular linear transformations. So the rank is the maximum possible, in this case, n. So the rank of this is going to be the rank of this because this has rank n. The same on the other side. The rank of that linear map is the same as this one because this is a bijection, this is a bijection. Hence, the rank at B is the same as the rank at AB, where A and B are any non-singular matrices. Thus, F has a constant rank not only on ON, but on all of this. The same conclusion that we had before for SL. Remember, for SL, the function had constant rank on every point of GL. Here, the same. For any matrix in GL, the differential will have the same rank. Hence, by the previous theorem, this is a submanifold. Right? Because we needed the function to have constant rank on a neighborhood of ON. And we do. something that I forgot to say is the dimension. So before moving into that, let's see if there are any questions.
So far, so good.
Good. So in order to know the dimension of ON, I need to know what is the rank. Okay. Now, how do we compute the rank? I forgot to do that. So this is my function. It maps the matrix X to X times X transpose. So in particular, this maps to this one, right? So I think I need to pick a matrix which is more easier to compute the rank. So I think that this is more easy to do with this. Because we have an automorphism like this. So it is better to focus on this linear map to compute the rank of the function.
What's the P in this case?
The identity matrix,
All right.
right? The identity matrix goes to itself. I have this and this. Now remember that this GLN is because it is open in Rn squared. Right? So how do we compute the rank now? Remember also what we saw in the first attempt to show that On is a manifold. This matrix is symmetric. So basically here, try that the image of this map, the differential, is the linear subspace of symmetric matrices. Because this is a vector space, right? This vector space is precisely Rn squared, but maybe it is better to think as the matrices n by n matrices. I claim that the image of the differential will give you the subset of symmetric matrices.
Can you repeat that? I didn't
Right.
get that.
Using this identification, what I claim right? So using that the tangent space is just Euclidean space, Rn squared. And that the same has the set of all n by n matrices. I claim that the image is the set of symmetric matrices. Let's see. Well, I was trying to get another way, but okay. You have this. Think of that as a tangent vector. So it is here. I want a curve here such that when I do all of this, I will get this vector.
What do you mean by all of this? That
So remember how we compute the push forward using curves. So what I claim is I have this here, a vector. I have here P. We need a curve here. I don't care what is the tangent vector there. But when I compose with the function, I get a curve here so that the tangent vector is the one given at the beginning. Okay? So I need to give a curve here. In this case, P is P identity. I'm taking any vector meaning a symmetric matrix, in particular this one. Then you can find a curve here. When you compose, you get this. Okay, let's do it in dimension 2. I want a curve, so let's put okay. So at 0, I have the identity matrix. And then I have to multiply this right? This is the curve on the other side, and it's going to look like C1t squared plus I'm omitting the t. Oh wait, there's a mistake here. That is 3, right? No, C1, C2. So this is the curve at the identity. I apply the function. I get this curve. I only care that it goes through the identity. But now you need to take the derivative with respect to t, right? And what is the derivative? So it will give you 2. And so on. I want this to be 1, the rest 0, 0, and 0. When we evaluate at 0. For instance, here, what you know is C1 at 0 is 1, C2 at 0 is 0, 0, and 1. When you evaluate at 0, this is going to vanish. This is going to be equal to 1. So you have only 2 times the derivative. Okay. And now you have to, so basically it's only a condition on C1 that you care. So construct a curve by non-singular matrices such that when you apply the function, the tangent vector is 1, 0, 0, 0, 0. Okay? So this is one way of computing the rank of this. Now, there must be a different way using LA and RA. But let me think about how to do that. And that's because we are missing the dimension. Okay? We know that it is a submanifold ON, but we need to determine the dimension. And by using the result, we need to know what is the value of the K of the rank at any point. Because that will give us the codimension, and hence the dimension of ON. Great. Are there any more questions? So time's up. We're done here. So next time, we will prove this, the case of the Euclidean case, and that gives rise to this result. Is the same one but on manifolds, and we will prove this. This is called the constant rank theorem. Okay, so that's for next time. Questions? Right, so have a good weekend and see you next week.
You too. See you next week.
Yeah, bye.